Welcome to the Deep Dive, the place where we take complex, cutting-edge technology and really break down what's happening under the hood to make the abstract feel a bit more actionable.
Today, we're wrestling with this magnificent technical paradox that sits right at the heart of modern AI. Transfer learning. How do you take an absolutely colossal foundation model, think of OpenAI's Whisper, which was trained on something like 680,000 hours of audio?
An insane amount of data.
Just a staggering amount. And how do you effectively refine it using maybe 5-10 hours of your specific custom data?
It feels like trying to teach a supercomputer a single new dialect. It just sounds contradictory, right? You'd think that tiny new input would just get, overwhelmed or rejected by this vast existing memory.
It should, intuitively.
Yeah. So our core question for this deep dive is exactly that. When you feed it a handful of new words or specific accents or some niche technical jargon, how does gradient descent actually allow the model to reconcile this tiny new input against its gigantic knowledge base?
And what's the strategy that keeps you from destroying all that prior knowledge?
Exactly. How do you avoid just wrecking the whole thing?
That is our mission today. We are going to go beyond the conceptual level and really look at the architectural mechanics. We'll dive into how the complex network of weights inside a transformer is selectively updated, why that intense process on your GPU is actually way more efficient than it looks, and how this whole technique of fine-tuning leads to genuinely better personalized results.
Okay, let's unpack that core mystery first, because it taps into a kind of a historical fear in machine learning. When you start adding this new, very specific data to a general model, the biggest pitfall was always what the community called catastrophic forgetting.
Absolutely. Catastrophic forgetting is the fundamental tension here, and it was a massive, massive problem in earlier neural networks.
What does that mean in practice?
Well, the fear was that the optimization process, driven by your new small data set, would just completely overwrite the weights that held all that general knowledge. So if I train a model on 5 hours of, say, my technical audio,
you don't want it to suddenly forget how to transcribe, "Please pass the salt."
Exactly. You don't want it to become a brilliant technical transcriber, but a completely useless general-purpose ASR model. You don't want to erase those 680,000 hours of its memory.
Right. But you're saying this doesn't really happen anymore as long as you're careful. So how is that disaster avoided? How is it engineered out of the system?
The whole mechanism is really rooted in the mathematical process of fine-tuning itself. It leverages the fact that the huge pre-training phase has already done all the hard work. The key component, the thing that stops this forgetting, is a very deliberate decision about the learning rate, or LR.
Okay, let's put some numbers on that. So during that initial pre-training, when Whisper was learning from scratch, the learning rate was pretty high.
Yeah, relatively high, often in the range of 1E3, so 0.001, maybe 5E4. A high rate like that is like driving a massive bulldozer across what we call the loss landscape.
Which is this high-dimensional map of all the possible settings for the model's weights?
Exactly. And that high learning rate lets the model take these huge, aggressive steps to quickly find a good starting region, a vast optimal valley in that landscape.
And when we come along with our tiny 10-hour data set for fine-tuning, we're not driving a bulldozer anymore.
Precisely. And this is the architectural genius of it. When you fine-tune, you use learning rates that are typically 10, even 100 times smaller. We're talking about rates like 1E5, that's 0.000001, or maybe 1E4. The difference in scale is just crucial.
I want to challenge that, though. If my new data has these critical new words I need the model to learn, shouldn't I be aggressive? Why be so conservative? If the learning rate is that tiny, how does the model learn anything new against the inertia of all those old weights?
That is an excellent challenge, and it really gets to the heart of what gradient descent is doing here.
Yeah.
The conservatism is all about stabilization. Think about that loss landscape again. The pre-trained model found the best general valley. If we used a large learning rate, even for a few steps, we could just overshoot that valley completely.
And you'd land somewhere totally different.
You could land in a new, narrow, but ultimately much worse place. A suboptimal gorge. And that, right there, is catastrophic forgetting.
Ah, okay. So the small learning rate is the nudge. It makes sure we don't jump out of that globally good valley, but we just sort of refine our position inside it.
Exactly. We're using a scalpel or maybe a laser pointer, not a hammer. These tiny adjustments mean the updates to the model weights are incredibly small. We're changing the weight vector by these minute amounts, like adjusting a dial by 1 micron.
So it's very delicate.
Very. This low momentum lets the small data set define the specific local topography, the location of your custom word or accent, without messing up the large-scale topography, which is the universal rules of language and sound. The model is basically saying, I know the world generally, but for this little region of the loss function, I need to make these super specific micro adjustments.
That makes perfect sense. The small data set is enough for that local tweak because the big data set already did the heavy lifting of finding the right neighborhood. But I mean, the model is a massive structure, a transformer with 30 plus layers. Is this micro adjustment happening uniformly across the whole thing?
Not at all. And this is where the design of the transformer architecture gives us another layer of protection against that forgetting. This brings us to what we call layer-wise learning dynamics, the idea that knowledge is kind of physically segregated in the network.
Okay, so where does our tiny update data have the most impact?
We see this really clear division of labor in the model, and it separates the universal features from the domain-specific mapping.
How so?
So think about the early encoder layers, maybe layers 1 through 4. These are the acoustic processing layers. They learn the really basic universal stuff like phonemes, acoustic patterns, noise, the fundamental frequencies of human speech.
Things that are true for pretty much any voice.
Right. Since your voice, structurally, isn't that different from the other 680,000 hours of audio in terms of sound waves, these foundational layers need very little adjustment. They might get, on average, a 0.1% to 1% change in their weights. That foundational acoustic knowledge is intentionally kept almost exactly as it is.
So the model still knows what a key sound is, whether I'm saying potato or some technical term like PyTorch.
Correct. The real action, where your custom data really argues most effectively against the existing linguistic preferences, that happens in the deeper layers, the later encoder layers, and especially the decoder and the final output layers.
Okay, and what do they do?
Those are responsible for the language model parts, the vocabulary mapping, the context, and ultimately picking the final word tokens.
And those layers, the ones holding the keys to vocabulary and grammar, they're the ones that soak up the custom data most aggressively.
Precisely. They're highly domain-specific. This is where your custom vocabulary, your specific way of code switching, the idiosyncratic spelling of your company's acronyms, that's where it all gets instilled. The updates here can be much more significant, often seeing 10% to 30% changes in their weights. This selective, non-uniform updating is the critical second pillar of efficient fine-tuning.
That is incredibly elegant. It's like you're applying a small patch to the engine block, the universal sound features, but you're completely replacing the steering wheel and the navigation system, which is the vocabulary and language mapping.
That's a perfect analogy.
But this process, it still involves calculating gradients for a massive number of weights, which has to be resource intensive. How has the community pushed this efficiency even further, especially for people on, consumer hardware?
That leads us directly to the cutting edge, which is LoRa, or low-rank adaptation. LoRa is this method that just makes fine-tuning these massive models computationally feasible for almost everyone. It's a genius concept for reducing the number of trainable parameters by like a factor of 100 or even more.
Remind us of the mechanism. We have this original giant weight matrix, let's call it W. How does LoRa get around retraining all of W?
Right. So when we train a big transformer model, we're operating on these massive weight matrices, W, that can have billions of parameters. Instead of calculating the gradient and updating all those values directly, which eats up a ton of memory and compute, LoRa just freezes the original W matrix completely.
It doesn't touch it at all.
Not at all. It then introduces two much, much smaller matrices, A and B, which are added to the system.
Okay, so W stays pristine, and we only train these two little matrices, A and B. But mathematically, how does training two tiny matrices substitute for updating one massive one?
That's the key, the low-rank part of the name. If you multiply matrix A by matrix B, the resulting product approximates the change, the delta W, that we would have calculated and applied to W directly in standard fine-tuning. LoRa's core argument is that these necessary task-specific updates are mathematically low-rank.
What does low rank mean in plain terms?
It basically means the complex change needed for a specific task-like learning to transcribe the name Gordievsky correctly can be described using far fewer dimensions than the original universal knowledge base. The rank of those adapter matrices, A and B, is usually very small, maybe 8 or 16.
Okay.
And because that rank is so low, A and B together contain maybe 100 times fewer trainable parameters than the original W. We're freezing billions of parameters and only training a few million new ones.
So we're not corrupting the baseline knowledge at all. We're just adding this highly efficient, mathematically precise preference layer on top. My preference for C-Translate 2 over C-Translate 2 is encoded entirely within those tiny A and B matrices.
Precisely. It adds a contextual preference without ever touching the foundational W. For example, if you're code switching between English and Hebrew, LoRa lets the model learn that when a certain acoustic pattern mekalet appears in an English context, the output should be the Hebrew word, not some forced English sound alike. It makes the whole process dramatically faster, slashes the VRAM you need, and most importantly, it mathematically guarantees you're preserving W's general knowledge.
Part 1 clarified the architectural magic that makes all this stable. Now let's talk practical strategy. For the average listener who has, a unique voice, a specific accent, or uses domain-specific language, is adapting a model really worth the effort? Or is the stock Whisper large model just good enough?
Oh, it's absolutely worth the effort because the general models struggle precisely where personalization is needed most. We're talking about edge cases that are common in your daily life but are, statistically almost invisible across 680,000 hours of general data.
Let's focus on the first big failure mode you see. Code switching adaptation. This is super common for bilingual or multilingual speakers who mix languages in the middle of a sentence. General models just seem to break when this happens.
They don't just break. They commit these fundamental transcription errors because of how they were trained. General models are usually trained on these massive, separate monolingual data sets. So when an utterance comes in, the model tries to identify the dominant language, and then it just assumes the entire sentence will follow that language's rules.
But if I switch mid-sentence from English to, say, some technical German terms, the model just gets lost.
Yes. It might try to force the German word into a phonetically similar English word, which generates gibberish, or it might incorrectly trigger a full language switch, meaning the rest of your English sentence is now transcribed with German grammar rules, which completely breaks the coherence. It's based on this outdated assumption of monolingual purity in speech.
And fine-tuning changes that assumption.
It does. By giving it targeted, high-quality examples of your specific mixed language pattern, your English-German mix, your English-Hebrew mix fine-tuning, tells the model, hey, this is a valid sequence.
Yeah.
It creates the contextual preference needed to pick the right foreign word token, even when the rest of the sentence is in the dominant language. It's essentially patching the model's linguistic assumption layer.
Okay, the second area is technical vocabulary. I'm thinking about acronyms and domain-specific terms that sound like other words in English, like ROCM versus ROCM or C-Translate 2.
This is critical for any technical user.
Yeah.
The general model just operates on statistical likelihood. It's probably seen the word cooler a million times in transcripts about heat or drinks. But maybe it's only seen cedia a few thousand times in some niche programming docs.
So when the sound is ambiguous...
And homophones are acoustically ambiguous, the large model defaults to the most frequent general option it knows. It defaults to cooler. Fine-tuning reverses that contextual preference. 10 hours of your specific tech-heavy speech where SUD appears over and over in the context of GPUs, it overrides the model's general preference. The small dataset doesn't teach the model what a GPU is, but it teaches it the probability mapping. In this domain, when you hear that sound, you should choose the low-frequency technical word. And it also enforces the correct capitalization and spelling, which is non-negotiable in technical docs.
This brings us to a strategic point that I find fascinating, especially for users who are running ASR on consumer hardware, an AMD GPU or just a laptop. The source material argues that fine-tuning a smaller model, like Whisper Small, is actually a better strategy than relying on a big stock model like medium or large that you might only get through an expensive API.
Yes.
That sounds counterintuitive. Why would a small model, even a fine-tuned one, beat a stock medium model?
This is the critical crossover effect in action. And it really just comes down to the math of improvement. We measure accuracy using something called word error rate, or WER. So let's just establish some baselines. A stock large model might have a WER of 5% on general speech. A stock small model might start at a WER of, say, 12%.
Okay, so the large model is clearly better right out of the box.
Yes, but the large model, because it's already so good, has less room to improve. If you fine-tune it, you might reduce its WER from 5% down to 3.5%. That's an absolute gain of 1.5 percentage points. It's a great result, but it took a huge investment in training resources.
Okay.
Now look at the small model starting at 12%. Because it's a fundamentally simpler model, its error function is shallower and it's easier to influence. A good fine-tune, specialized for your unique vocabulary, might slash its whir from 12% all the way down to 6%.
Hmm.
That is a massive absolute gain of 6 percentage points.
Ah, I see the light. The absolute gain is much bigger for the smaller model, so the relative improvement, the percentage of errors you get rid of, can be 30% to 50% for the small versus maybe 15% for the large.
Exactly. And because of that high potential for relative improvement, your customized Whisper Small model, specialized for your voice and your domain, can genuinely approach or even match the performance of a stock, off-the-shelf Whisper Medium model when you test it on your specific data.
So you get near medium accuracy, which is excellent, but you get all the benefits of running a smaller model locally. You get faster inference, way lower power consumption, total privacy because your data never leaves your machine, and critically, zero ongoing API costs. That seems like an undeniable optimal strategy for the solo practitioner.
It really is. It shifts the user from being just a cloud service consumer to being an owner of a highly optimized, specialized tool. It's the highest return on investment for personalization in ASR right now.
Moving on to something adjacent, readability. A huge part of a perfect transcript is punctuation, and the source material correctly points out that punctuation style can be really idiosyncratic. How I use commas, whether I prefer an em dash, might be very different from standard journalistic style. Can we fine-tune an ASR model for that kind of stylistic consistency?
This is a tricky area, and it really highlights the limitations of training just on acoustic data. While integrated models like Whisper do try to use acoustic cues like tiny pauses, shifts in prosody, changes in pitch to predict commas and periods, fine-tuning an ASR model for stylistic consistency is extremely difficult with just a few hours of speech.
Why is that so hard? I mean, doesn't my voice carry that information?
The information is just too sparse and ambiguous. You might pause for half a second to take a breath, and Whisper might interpret that as a period or a comma or maybe nothing at all. The statistical frequency of a comma is just so low compared to the frequency of words. To learn my preferred comma usage, the linguistic preference, not the acoustic cue, you'd need a huge body of text examples.
So relying on 5 hours of speech to define my unique punctuation style is a losing battle. What's the smarter, more practical approach?
The superior approach is model orchestration. You decouple the problem, you use the ASR model, whether it's stock or fine-tuned for vocabulary, to generate the raw, unpunctuated lowercase text output.
Okay, so you get the raw words first.
Then, you fine-tune a separate, specialized component, a small punctuation restoration model. Usually this is a dedicated language model like a small BERT or a smaller GPT.
And what data do you feed that model?
You train that punctuation model on a massive body of your existing written work. We're talking 50,000, 100,000 words or more. This lets the model learn your specific linguistic patterns, your preference for coordinating conjunctions, your high comma frequency, your use of dashes, or your love of short, punchy sentences. This customization is orders of magnitude more effective for style than relying on the ambiguous acoustic data from your speech.
That is brilliant. It's using the right tool for the job. The ASR handles the tricky acoustic-to-text conversion, and a separate, dedicated language model handles the grammar and style based on your written history.
Exactly.
Okay, we've established that fine-tuning is valuable, but the whole process lives or dies on the quality and volume of your training data. For someone starting this journey, let's talk volume. What is the practical minimum of custom data you need to see a genuinely noticeable improvement in your word error rate?
As a starting point, the absolute bare minimum to just test the pipeline is maybe 30 to 60 minutes of carefully transcribed audio. But for practical, observable improvement that translates into real-world gains, the sweet spot for fine-tuning, you really need 2 to 5 hours of high-quality, accurately transcribed audio.
And that's enough for the model to learn your voice.
It's enough for the model to learn the basic acoustic features of your voice and maybe a handful of your key vocabulary terms.
And if you're aiming for something more robust, like for a financial analyst or a heavy tech programmer, what's the recommended volume then?
For solid domain adaptation, we'd recommend aiming for 10 to 20 hours. At that volume, the model has enough examples to actually generalize those new concepts, not just memorize them. But volume alone isn't enough. The diversity within that small data set is just as critical to prevent overfitting.
How do you introduce diversity when the whole point of the fine-tune is to specialize in my voice and my domain?
You need 2 types of diversity. First, speaker diversity, if you can get it. If you can include a small percentage of other people speaking the exact same custom vocabulary, maybe colleagues or guests on a show, It teaches the model that those technical terms aren't just tied to your unique voice, but that they're acoustic concepts that generalize across speakers.
And the second type.
Acoustic variety. Make sure your 10 hours aren't all recorded on the same mic in the same quiet room. Use a mix of your desktop mic, your phone, maybe a slightly different room environment. This ensures the model isn't just hopelessly overfitting to one specific recording setup.
This brings us to a really counterintuitive, almost paradoxical point from the source material, the clean data paradox. If I, the listener, primarily use ASR in noisy real-world conditions, a busy office, a loud coffee shop, my first instinct is to train the model on audio recorded in those exact noisy conditions. But the sources argue that's actually the wrong approach. Why?
That intuition, while it's totally logical, leads to a brittle, suboptimal model. If you record natively noisy audio for your small 10-hour data set, the noise is inconsistent. Every sample has different random high variability noise, a siren here, a car horn there, a door slamming.
Okay.
So given the model's small training budget, those 10 hours, it has to split its already limited capacity. It has to try and learn the clean signal of your voice and simultaneously try to learn how to ignore all that random noise. It ends up learning both tasks poorly.
And the result is a model that's not good at either.
Right. You get a model that's great at transcribing your voice in that one specific cafe on a Tuesday afternoon, but it fails when you're speaking clearly in a quiet office.
So what's the winning strategy? How do we teach it robustness without confusing it?
The winning strategy is to decouple signal learning from noise robustness learning. You primarily record pristine, clean audio, at least 30 decibels signal-to-noise ratio in a quiet environment. This clean audio is your gold standard base. This lets the model lock on to the fundamental acoustic features of your voice and vocabulary without any interference.
And then you introduce the noise systematically.
Precisely. Use that clean audio as a base, and then you apply controlled, programmatic data augmentation. This means you digitally inject various forms of synthesized or recorded noise, white noise, fan noise, simulated room reverberation at consistent controlled levels.
So you're teaching it in stages.
Yes. This strategy teaches the model the clean signal of your voice first, and then it teaches it noise robustness separately, using diverse but structured variables. The model learns this is the sound of the word C translate to, and here are 10,000 ways it can be corrupted by ambient noise, but the underlying signal is always the same. It leads to far better generalization.
That is significantly more elegant than just relying on the random chaos of the real world. Now let's talk structure, and the most famous constraint of Whisper, the 30-second audio chunk limit. We see this limit everywhere, but why does it exist, and how does it affect our data preparation?
The 30-second limit is not arbitrary, and it's not a simple software default. It is a hard architectural constraint tied directly to the transformer design and how it was trained. It's linked to the model's fixed Mel spectrogram input size and, critically, the memory limitations of the attention mechanism.
Can you elaborate on that memory limitation? Why does audio length kill the memory?
It all comes down to the scaling behavior of the transformer's attention block, which is the core of its intelligence. The computation and memory you need scales quadratically, that's O of n squared, with the length of the input sequence.
So it's not a linear increase.
Not at all. If you double the length of the audio from 30 seconds to 60 seconds, you don't just double the memory required, you increase it by a factor of 4. If you go to under 20 seconds, you increase it by a factor of 16.
And that quickly becomes computationally impossible on standard GPUs.
Exactly. 30 seconds was chosen by the designers as the optimal sweet spot. It gives enough context for the model to predict words and follow prosody, while making sure the model could be trained and, critically, run efficiently on consumer and cloud GPUs without instantly hitting a memory wall.
So for our fine-tuning data, we are absolutely stuck with 30-second chunks, maximum.
Yes. Any samples longer than 30 seconds will either get truncated by the training script or just rejected because they won't fit the fixed input size. The optimal length for preparing fine-tuning data is somewhere between 10 and 30 seconds. And critically, longer chunks, closer to that 30-second limit, are better.
Why is 25 seconds better than 5 seconds?
Context. Longer chunks capture natural narrative flow, prosody, and the linguistic context that the model needs for accurate transcription. 5-second snippets are often just too short to establish a subject, verb, and object, and that leads to fragmented context and poorer performance in the decoder layer.
So aim for long sentences, but cut them off before 30 seconds.
Ideally, you segment in natural sentence breaks. but ensure those segments are as long as possible up to that 30-second ceiling.
We often experience this limit during live transcription or voice typing, where the text just appears choppy.
That choppiness is the direct result of that sequential processing hitting the 30-second boundary. The application stops the audio stream, sends the 30-second buffer for inference, waits for that burst of processing, prints the text, and then restarts the whole cycle. It forces these arbitrary breaks.
And how does professional batch transcription, where you process a whole pre-recorded file, handle this better?
Batch mode is much more optimized. First, you can look ahead and use the entire file to find natural segmentation boundaries, pauses, sentence endings, instead of just arbitrarily cutting at 30 seconds. And second, crucially, it uses overlapping chunks and parallel processing. It might process chunks 0:30, 20:50, and 40:70 all at the same time. This dramatically increases speed and minimizes errors at the boundaries, giving a much smoother, higher quality result.
Okay, we've talked a lot about the computation needed for all this. This brings us to a huge hardware reality check that I know generates a lot of anxiety for users running these models locally. The misconception of 100% GPU utilization.
This is one of the biggest and most understandable sources of confusion, especially for listeners who come from, say, a PC gaming background. A user runs their fine-tuned Whisper model and sees their GPU utilization suddenly spike to 98%, 100% during that transcription burst.
And their immediate panicked thought is, I'm bottlenecked, my GPU is too weak, I need a bigger card.
Exactly. But what's the reality here? Is 100% utilization a failure state in AI inference, like it might be in rendering a game?
It sounds bad.
Absolutely not. In AI inference, 100% GPU usage during that processing burst is not only optimal, it is the fundamental goal. It's a sign of a healthy, efficient workload. It means you are leveraging the hardware you paid for perfectly.
Explain the difference between this and a gaming workload.
In gaming, the GPU is render-bound. Continuous 100% usage means the GPU is failing to calculate the next frame fast enough, which results in frame drops or latency. The workload is continuous. But in AI, especially ASR inference, the workload is compute-bound and it's highly bursty.
What does it mean, bursty?
The model needs all its millions of matrix multiplications to be executed as fast as possible in one single coherent sequence. We call it the forward pass. When the model runs that calculation, it wants to leverage every single available CUDA core or compute unit. That calculation takes a very short time, often less than a second, for a 30-second chunk on modern hardware. During that short burst, it should hit 100% utilization.
So the spike means the model is aggressively using its resources to finish the task faster, not that it's struggling.
Precisely. After that half-second or 1-second calculation is done, the GPU utilization immediately drops back down to idle while the CPU gets the next audio chunk ready. If your GPU was only hitting 50% utilization, that would actually be inefficient. Half your expensive compute resources would be sitting idle. Seeing 100% means you have a highly optimized inference engine.
That is a critical distinction that could save a lot of listeners some unnecessary upgrade costs. Now let's tackle the elephant in the room for a lot of DIY AI users, the AMD and ROCm ecosystem. It has historically been a significant pain point for running open source models.
It has been a source of great friction, yes. AMD's ROCm support for AI has historically lagged well behind NVIDIA's CUDA ecosystem. CUDA is mature, it's widely adopted, and nearly all open source models are natively built for it. This means trying to use the standard PyTorch implementation of Whisper directly on AMD hardware often results in poor performance, bugs, or just silently falls back to the CPU.
So for AMD GPU users running their newly fine-tuned small model, what is the recommended, highly reliable engine?
The clear Tier 1 recommended choice for fast, reliable AMD acceleration is Faster Whisper. This engine uses the cTranslate 2 backend. cTranslate 2 is an inference engine built from the ground up to optimize transformer performance, with a specific focus on things like quantization, bean search, and low latency inference.
And it works well with AMD.
It has excellent, officially supported ROCm compatibility, which often simplifies the setup process immensely. On top of that, because it's so optimized for this kind of workload, it typically offers 3 to 4 times faster inference performance than the original unoptimized OpenAI PyTorch code, all while maintaining the accuracy of your fine-tuned model.
So if I'm on an AMD card, Faster Whisper and cTranslate 2 is the production-ready path. What about other popular options like Whisper.cpp?
Whisper.cpp is a brilliant piece of engineering, and it's highly optimized for CPU-only performance using the ggml or gguf format. It's fast and low memory on a CPU. However, its AMD GPU support through the HIP stack is experimental. It often requires specific manual compilation and configuration that can be frustratingly brittle for production use.
So it might just not work.
A common failure mode for Whisper.cpp on AMD is that if the GPU initialization fails for any reason, a driver mismatch, a missing library, it often just silently falls back to the CPU. The user gets confused because they see the process running, but they aren't getting the GPU acceleration they expected. For robust high-speed ASR, C-Translate 2 is the superior choice for AMD GPUs.
Okay, so once a user has successfully fine-tuned their model, which is probably stored in the native PyTorch or SafeTensors format, they need to convert it for optimal deployment. What are the target formats for a custom model?
The need for conversion is absolute. Running native PyTorch models directly for inference is slow and inefficient. We really look at two primary target formats depending on the deployment goal.
What's the first one?
For desktop or server optimization, where you're aiming for maximum speed on a GPU, whether it's NVIDIA or AMD via C-Translate 2, the target format should be C-Translate 2. This is the format that the faster Whisper engine consumes. It allows for highly efficient static quantization, which reduces the model size without a big accuracy loss, and it ensures all the performance optimizations built into C-Translate 2 are used.
And what if they want to deploy their fine-tuned model on a resource-constrained device, like an older laptop or a phone, using only the CPU?
For that edge or CPU-only optimization, the target format should be GGUF, the GGML universal format. This is the official successor to the legacy GGML format that powers the entire llama.cpp ecosystem.
We hear a lot about GGUF these days. What makes it fundamentally better than the old GGML format for a robust deployment?
It's all about robustness and maintainability, which is vital when you're sharing or deploying custom models. GGUF embeds comprehensive model metadata directly into the file structure itself. This includes architecture details, tokenizer information, and most importantly, the exact quantization parameters like Q40 or Q8.
How did the old format work?
The old GGML format required the user or the loading script to manually track all those settings. If you loaded a model with the wrong quantization setting, it could either fail or, worse, give you silent, inaccurate results. GGUF makes the model self-describing. When you load a GGUF file, the program immediately knows exactly what quantization level it is, what architecture it belongs to, and how to initialize the tokenizer. This reliability makes it the gold standard for robust, maintainable, CPU-only deployment.
This deep dive has shown us that fine-tuning Whisper isn't an act of brute force at all. It's an architectural refinement enabled by a series of precisely controlled, clever mechanisms. We use tiny learning rates to stabilize that massive knowledge base.
And highly specialized, efficient components like Loros to add new, low-rank contextual preferences without ever corrupting the original weights.
And we established that for the individual user, the fine-tuned small model is the strategic winner. It's a genuine competitor to the stock medium model for personalized use, offering the best balance of speed, accuracy, and local private inference.
Especially when it's deployed through optimized engines like faster Whisper and formats like C-Translate 2.
We also cleared up that hardware confusion. Seeing your GPU spike to 100% during inference is not a cause for panic, but a sign of a highly efficient workload. And remember that data paradox. Train clean and augment your noise programmatically to get the best generalization.
We focus today on personal optimization, where lowering your WAR from 8% to 5% can dramatically improve your daily workflow. But let's leave you with a final provocative thought that places this entire discussion in a larger context. What happens when accuracy is truly mission critical? When a transcription error isn't just an annoyance, but a literal life or death scenario?
You're talking about high-stakes medical transcription, surgical documentation, or real-time air traffic control ASR.
Exactly. These mission-critical systems simply cannot rely on an off-the-shelf Whisper or a few hours of personal fine-tuning, no matter how clever the Lori implementation is.
So what do?
These high-stakes enterprises don't view ASR as a model to be downloaded, but as infrastructure to be built. They commit to custom ASR pipelines that often take 2 to 4 years to develop and deploy, costing millions of dollars. Their specialization involves continuous improvement loops, using proprietary gold-standard datasets that often exceed 100 hours of annotated audio, and they focus relentlessly on achieving verified sub-3% word error rates.
Wow.
It illustrates that while transfer learning offers this brilliant efficiency for personal use, the true frontier of extreme accuracy in ASR isn't just in optimizing the transformer weights themselves. It's in the long-term, expensive, and dedicated infrastructure built around constant human validation, auditing, and continuous improvement needed to meet those mission-critical thresholds. It shows you just how far the gap remains between consumer-grade and true enterprise-grade ASR.